Today we're looking at matrix transformations. So taking all the information we know about transformations, and at the moment particularly looking at reflections and dilations, we're going to have a look at how this information might be presented in the form of a matrix equation, and also how this might be applied when finding the image of a curve undergoing such a transformation. So the first thing we should have a look at here in the table is talking about the ways in which we might represent transformations such as reflections and dilations. Now looking at the bottom here, we can see, I'll just star it so we know what we're talking about. Most transformation equations take this form. So we start off with a dilation matrix. Now this is a 2 by 2 matrix, and this represents all the dilations and reflections that can be applied to x and y. Our x and y here are our variables, and we're saying that when we transform these variables, we'll end up with new ones, which we denote as x dash and y dash. Now we can find these new x and this new y, or these new variables, by first applying that dilation and any reflections at the same time, followed by adding our translation matrix. Now this one is a 2 by 1. So what do these look like? Well, if we're reflecting in the x-axis, as we can see up here, we'll see a negative down in the bottom right hand corner of the matrix. You'll see this as we multiply it by x and y, but really what we're saying here is take the y values and multiply them by -1. If we negate all the y values, but keep all the x values the same, we would be reflecting in the x-axis, or reflecting about the x-axis. If we're reflecting in the y-axis, it's a very similar case, but you'll notice that the negative appears in the top left-hand corner. This is because a reflection in the y-axis quite literally takes all of the x values and negates them. Now the really good thing about a dilation matrix is that we can see down the bottom here, dilation by factor k from the y-axis. And the good news here is that we don't have to think about doing 1 on k, or as we've been using the notation, 1 on n. Here, if we see a number, then we literally refer to that number as a dilation of that factor from the y-axis. So a dilation factor of 3 from the y-axis literally takes each x value and multiplies it by 3. Functionally though, this would be the equivalent of subbing in x over 3, and you'll see later how this works out. If we're referring to a dilation factor from the x-axis, we know that just like the reflection about the x-axis, our factor will appear in the bottom right-hand corner. Now you notice that dilation matrices all have a very common theme here, and that's that the anti-diagonal are all zeros. If we had the opposite case, in which the leading diagonal was 0, we'd call this a reflection in the line y equals x. And of course you may notice that this would be swapping x and y, or as we like to call it, finding the inverse function. Now looking at how this applies to an example, it says the following matrix equation was applied to the function y equals x cubed. So if we had a transformation applied to a function, as we can see here, we know that y equals x cubed must indeed be the pre-image. So we might as well label that now. We can see that the following matrix equation, well, what are we talking about here? That's this matrix equation. So this is a series of transformations that have been applied to x and y in order to find a new x and a new y. Now the question asks us to find the rule of the transform function. So the transform function here is saying find the rule of the image. And it's also asking us to describe the transformations applied. And again, here is a little clue where it says applied to y equals x cubed, telling us that that must indeed be the pre-image. So the first thing we want to do is evaluate the matrix. Now specifically, we're going to look at this and we're going to think, evaluate the dilations and translations. So let's write that down. We've got our 2, 0, 0, negative 1 times xy plus negative 4, 0. So if we multiply this, we'd get 2 times x plus 0y, so that would be 2x, and 0 times x minus y, so that would be negative y. Now we still need to add negative 4 and 0 to the mix, and so when I evaluate that, I'll get 2x minus 4, negative y plus 0, and that's at matrix dilations and translations evaluated. We know that once these transformations have been applied, it's true to say that 2x minus 4, negative y, is equal to my new x and my new y. So our next step here is to equate the two elements. That is, 2x minus 4 is equal to x dash, and negative y is equal to y dash. While this is true, it's not very useful to us. In order for it to be useful, we ought to solve for our x and our y in terms of our new x and new y. So here we might just think solve for x. The y equation is easy. We'll multiply both by negative 1, so that y is equal to negative y dash. Here, 2x is equal to x dash plus 4, which we can achieve by adding 4 to both sides. And if we divide by 2, x is equal to x dash plus 4 over 2. The reason why we're solving for x and y is that we now have something to substitute into our pre-image. Our pre-image was y equals x cubed. And so our image would be just a case of subbing in this here and that there. And so negative y dash is equal to x dash plus 4 on 2 all cubed. All we need to do now is multiply both sides by negative 1, and we know that our image y is equal to negative x dash plus 4 on 2 cubed. So this is us having found the image. However, there are two parts to this question. We found the rule of the transform function, which we know is the image, and we can see that here. But we also now need to describe the transformations applied to y equals x cubed. Now, looking at my image, this is certainly possible, although somewhat difficult. If we look at the matrix for the answers though, we know that we can't have made a mistake. The question isn't going to be wrong, but my working might be. So I might make sure that I'm referencing that table in the previous page, and I can see that in the matrix equation at the top, there's a 2 here. And I know that that's going to multiply all the x values by 2. And so we can describe that as a dilation from the y-axis by a factor of 2. Now this is much easier to see in the matrix than it is in the function. The function looks like everything's been divided by 2 down here. But of course we know that we read that as 1 on n. We can also see from the matrix equation that there's a negative 1 down here, which would be multiplying all the y values by negative 1. Once again, we can reference our table here to see that there is a reflection this will be about the x-axis as all the y values are changing. Finally, when we're looking at our translation matrix, we can see that there's no translation of y, as there's nothing being added to y, but there is a translation of -4 in the x. Now if we're subtracting 4, that means we're moving in the negative x direction, and so we describe this as a translation 4 units along the x-axis in the negative direction. Now that was generally the case and generally the process which we might use in order to find the image of a curve. But we can use the same thing in a simpler case where we're finding the image of a specific point. So looking at example 2, the question is really quite simple here. It's asking us to find the image. Now it's asking of the point 1, -3 under part A being a reflection in the x-axis. Now we might just recognise how this works, or we could do it more formally. We could say that a dilation matrix, which represents a reflection in the x-axis, is going to negate all the y values. Or if we just have a look at our table from page number 1, we know that there's a -1 here, a 1 here, and zeros along the antidiagonal. Now instead of multiplying by x and y, we know specifically that the ordinance is 1, -3. So we can say x is 1, y is -3. Now when I multiply that by 1 plus 0 times -3, we end up with an unchanged x. And when I multiply 0 by 1 and -1 by -3, we end up with a positive 3. And so the image of the point 1, -3 is 1, +3. This makes sense because a reflection in the x-axis literally means that we are negating all the y values. Now for part B, we can see that there's a dilation of factor 2 from the y. Now this might raise the question, do we multiply the x by 2 or do we multiply the x by 1/2? Well, we don't have to think about this if we do it the way matrices intend us to. A dilation factor 2 from the y would be a matrix equation in which we have 2, 0, 0, 1. We're not going to multiply it by x and y, we'll multiply it by 1, 3 because we're finding the image of a point, not the image of a curve. 2 times 1 plus 0 times 3 gives us the point 2, and 0 times 1 plus 1 times 3 gives us the point 3. And so we can see that our new coordinate, or the image of the point 1, -3, is 2, 3. You might also note that if we're dilating by a factor of 2 from the y-axis, this is doubling all of the x values. Finally, for part C, we're after a dilation factor k from the x-axis. And we don't know what k is, so we can anticipate that it will be part of our answer. If we're dilating from the x-axis, so there's that little word there, it means that our dilation factor will appear in the bottom right-hand corner. When we multiply this by 1, -3, we know that we will have the new point 1 times 1 plus 0 times -3 is 1. 0 times 1 minus 3 times k is -3k, and so our point becomes 1 minus 3k. And that's how we apply transformations to a point. In example 3, we're asked to really read the matrix equations. And by that, we can see that the question asks us to state the transformations associated with the following matrices. Now those matrices being here, here, and here. Well, the first thing we might have to recognise is the order. Given that part A is a 2 by 2 matrix, we know that this would be a dilation or reflection matrix. given that there's a negative 1 in the top left-hand corner, so that would apply to the x values, we know if we negate all the x, that must have been a reflection about the y-axis. We can also see that there's a 2 down bottom right-hand corner, so that's going to affect all the y values, which would imply that there's been a dilation of factor 2 from the x-axis. Looking at part B, similarly, we can see that there's a number 3 up in the top left-hand corner. So if we're multiplying all the x values by 3, that would be a dilation by a factor of 3. Changing all the x values means it must be happening from the y-axis. We can see that there's also a 4 here in the bottom right-hand corner, which implies a dilation of factor 4 from the x-axis. What we'd also note is that there's a negative here. Now if I'm negating all of the y values, then I must be reflecting, or it would be reflected, about the x-axis. Finally, in part C, we can see that the order is a 2 by 1. Now we note that if it's a 2 by 1, this must have been the translation component of the matrix equation. X is on top, y is on the bottom is a pretty reasonable assumption. And so we can see here that it's been translated 2 units left along the x-axis, or in the negative x direction. Just beneath that, we can see the number 7, and so we also know that that's been translated 7 units in the positive y direction. In example 4, we're asked to find the matrix equation that determines the following transformations. So we know that we're just being asked to find an equation and not actually solve it. We also know that it's in reference to the following transformations. So the first thing that I might start with is, what does a matrix equation actually look like? We know that it's going to be the transform of something, and it's reasonable to choose the values x and y. More on that in a moment. We know that that would be equal to a dilation matrix, which would be a 2 by 2, would be multiplied by x and y, and there's likely going to be a translation. Now the first transformation that we see is there's a dilation by factor 3 from the y-axis. So I'm looking here at a dilation by factor 3 from the y-axis. So we know we're talking about a dilation of 3 from the y-axis. Now that's going to change all of the x values, and in a matrix equation, the number is described exactly as we see it. So there's a 3 in the top right-hand corner. The next transformation that we're looking at is a reflection in the x-axis. Now if there's a reflection, and if we know it's in x, then that means that in the bottom right-hand corner there has to be a negative 1. We can assume zeros where we've got no additional information, and we can see that the final thing here is that it's translated, so there's a translation, of 1 in the positive direction of x. So we know that we can plus 1. And it's 2 units in the negative direction of the y, so we would minus 2. Now the key, I suppose, phrasing here is that we see this term followed by. I might actually just highlight it in black so that it stands out a little bit. The fact that the translations occur after the dilations and reflections is the reason why we can just use this standard transformation equation. Remember, we assume Dr. T. Finally, to round off this answer, we may choose to write in the fact that this could also be equal to nu x and nu y. In part B, we're also asked to find the matrix equation, But this time we can see that the phrasing says a translation of 1 unit right of the x-axis and 2 units up, followed by, so this happens after the translations now, so followed by a dilation by factor 3 from the y-axis and a reflection in the x-axis. So we can see that our normal, usual, I suppose, scaffold for a matrix equation is not going to apply. So we would have the transform of x and y, this time equal to a dilation that occurs after x and y has been translated. And so the brackets help here because we know our order of operations still hold true. BIDMAS, BEDMAS, BODMAS, however you've learnt it, it's still true for matrices. Now we can see here that there's a translation of 1 unit to the right, so I know that I've got a plus 1 on the x, and a translation of 2 units up. So I know I've got a plus 2 in the y. Now if we're followed by, that what's outside the brackets, a dilation by factor 3 from the y. So that means that in the top left-hand corner we'd have a 3, and a reflection in the x. In the bottom right-hand corner we'd have a negative 1. Now until we get well practiced at this, you may want to refer to the table at the start of the notes to help you complete these types of questions. Example 5 is similar to that first example, similar to our success criteria, that we're able to find the equation of an image undergoing a certain matrix transformation. So we can see here, setting the context, a transformation is defined by this matrix. We're being asked to find the equation of the image, well, the image is in reference to the thing that's happened after that transformation, of the graph with this equation. So the other thing here must be the pre-image, so the thing that happened before the transformation. Well, let's start with our matrix equation. So we want to set it up such that T of x and y is equal to our dilation matrix 2, 0, 0, negative 3 times x and y. There are no translations here, so I can ignore that part and immediately equate to new x and new y. I can see by multiplying this equation that we have 2x and negative 3y equal to x dash and y dash. So this is really my step 1, which was to evaluate the matrix equation. You may recall that our next step is to equate these to x dash and y dash, remembering to solve for x and solve for y. So 2x is equal to x dash, that's our top row. Now this implies that x is equal to x dash on 2. We can see that negative 3y is equal to y dash, and so y is equal to y dash on negative 3. We can see here that this was our solving for x and solving for y in terms of x dash and y dash. Once we've done that solving, we can substitute these into our pre-image y equals x squared plus 2x plus 3. So we can see here, instead of our y, we have y dash on negative 3. And instead of x being squared, we'll just put some brackets around that, because we'll have x dash on 2 squared. We don't have 2x, instead we have 2 times x on 2. And then that's just plus 3. So we can evaluate this and say that y dash on 3 is equal to, well, we don't need the dashes anymore, so we might as well rub those out to make things easier. And we'll have x squared on 4, because the squared needs to apply to the fraction as a whole. That means the numerator and the denominator. If we've got 2 times x on 2, then of course we just have x, because these will cancel. And the plus 3 remains unchanged. Our final step is to get y on its own, which would require multiplying by negative 3. And so we can make our answer, just up here, y equals negative 3x squared on 4 minus 3x minus 9. And that's the equation of the image under that transformation. New x and new y. Here we have a particularly difficult question. We start with a bit of context that a transformation is defined by this matrix. It says that the image of a curve with equation y equals 2x squared plus 1. So that means the pre-image is 2x squared plus 1, and the image of this curve under such a transformation is y equals ax squared plus bx plus c. So we don't know what the image is. But our task is to find the values of a, b, and c. Now something like this might commonly be a calculator question, and so we can have a look. We're not going to change the way we approach it because we actually still need to find the image. It's just that once we've found it and totally expanded it, we'll be able to equate our a, b, and c to the relevant coefficients. Well, let's start with our matrix equation, and as usual we're going to evaluate the matrix. When we do so, we get 3x and 2y. If we're minusing 1 and adding 4, we can say 3x minus 1 and 2y plus 4 is equal to new x and new y. If we equate these two equations, 3x minus 1 equals x dash, 2y plus 4 equals y dash. Solving for x and y, I can see here that x is equal to new x plus 1 on 3, and y is equal to new y minus 4 on 2. If we're going to sub that into the equation y equals 2x squared plus 1, we can see that y dash minus 4 on 2 equals 2 times something squared plus 1, and of course that something is x dash plus 1 on 3. Once we've done this, it's really good habits just to make sure that we're now in a position to rub out the dashes, and so we'll do that. Now in order to solve this, we're going to have to expand that square, multiply by 2, add 4, and that's quite arduous. It's why these kinds of questions are usually in the calc. We can use our calculator to expand. Now of course I wouldn't be writing this down, this is just for our learning, but we do menu, algebra, expand. Or we could go menu, algebra, solve for y. And what we'll find is y equals 4x squared on 9 plus 8x on 9 plus 58 on 9. Now although we found the image of the curve, what we were actually asked to do, which we can see over here, was find the values of a, b, and c, knowing that the image takes the form y equals ax squared plus bx plus c. So all we have to do now is recognise that our coefficient 4 over 9 is here. It's a. So I can state that a equals 4 over 9. Our coefficient of x, which is labelled b in the question, we found to be 8 over 9. And so we conclude that b equals 8 over 9. At this point, I'm hoping you can see that our final value of c must be 58 on 9. Now this question can certainly be done by hand, although the algebra can be quite arduous, and it's what we might expect to be on a calculator active question. The final question comes from a past VCAR exam in 2010. It says, find the equation of the image y equals 1 on x under the transformation defined by the matrix 2, 0, 0, negative 3, and describe a sequence of transformation that maps the graph of y equals 1 on x onto the graph of its image. So very similar to what we're used to, we need to find an image and we need to state the sequence of transformations. We might start by scanning the question and saying, okay, what are the pieces that I have here? Well, I know I've got the pre-image, y equals 1 on x, the transformation, 2, 0, 0, negative 3, and I need to find the equation of the image. The second part is to describe a sequence of transformations that makes this possible. So, starting with our matrices, we've got 2, 0, 0, negative 3 times xy is equal to mu x and mu y. If we evaluate the matrix, we get 2x and negative 3y equal to x dash y dash. Following our same formula, we can now equate 2x to x dash, solving for our old x, and negative 3y to y dash, solving for our original y. Now once we've got this, we want to sub it into the pre-image being y equals 1 on x. So instead of y, we've got y on negative 3. And instead of x, we've got x dash on 2. Now that means that the 2 is going to come all the way up there, and we're going to multiply by negative 3, so that y is equal to negative 6 over x. Now here we might look at y equals negative 6 over x, and a sequence of transformations could absolutely be that we reflect in the x-axis, or we reflect in the y-axis, and dilate by a factor of 6 from the x, or indeed 6 from the y. All of these are possible, but it's usually best to look to the question. And if we see on the question there, we can see that there's been a dilation of factor 2 from the y-axis, and a dilation factor 3 from the x, followed by a reflection about the x-axis. And so this is how we describe the transformations. And that's it for matrix transformations.